Good day to all. So it's chemistry time once again. This time we are going to talk about chemical bonds. So for our objectives, draw the Lewis structure of ions. Second, apply the Octet rule in the formation of molecular covalent compounds. Third, write a formula of molecular compounds formed by nonmetallic elements of the representative blocks. Draw Lewis structure of molecular covalent compounds. Describe the geometry of simple compounds, and last, determine the polarity of simple molecules. So to start with, we are going to talk about electron dot structure. So it was Gilbert Newton Lewis. He proposed a system to emphasize atoms' valence electron. Take note of valence electron. These are the electrons found at the outermost energy level, and this is the combining power of the compound. So how he emphasized valence electron. So with the use of LEDs, stands for Lewis electron dot structure. So this is a shorthand to represent the valence electrons of an atom. This consists of elements symbol, which represents the nucleus of the atom, and the dots, which represent the valence electrons. So valence electrons are represented by dots. And this is how he makes use of that to represent valence electrons. So these are the families or the representative elements. So we have family 1A, so they have one valence electron, so we have one dot. Family 2A, two valence electron, two dots. 3A, three valence electron. And of course, we have halogens, 7 valence electrons, so there are 7 dots. And finally, for noble gases, which of course, this is the family with a stable configuration. They are stable, okay? And they have a complete uh, electron configuration, or 8 valence electron, okay? So this is all about the LEDs. Take note of the symbol, the nucleus of the atom, and the dots, which represents the valence electron. Okay, so this LEDs is actually very useful in understanding about chemical bonds. So what are chemical bonds? These are forces of attraction between two atoms or ions. And there are two types. We have covalent and ionic. So ionic is the transfer of electrons, and for covalent we have sharing of electrons. Why do atoms transfer electron, and why do atoms share their electrons? Of course, to achieve stability. Take note, stability of atom is achieved by having a complete 8 valence electrons. So we call it as rule of the 8, octet rule. So for ionic bond, take note of the positive ion formation and the negative ion formation. So how an atom acquire a positive charge and how an atom acquire a negative charge. So this is from the very beginning, it's very clear that we have two kinds of ion. So we have the cation. Okay, we have the positively charged ion. So how an atom acquire that positive charge? They lose electron. Okay, so typical examples are the elements found in group 1. So they lose one electron to acquire a charge of positive 1. So for family 2A or group 2, they lose 2 of its electrons or the valence electron and acquire a charge of positive 2. Same as with family 13 or 3A, they lose 3 electrons to acquire a charge of positive 3. Okay? On the other hand, we have, okay, before we go to that, let's have first the example for the positive ion formation. So for lithium ion here, 1s2 to s1. So its valence electron is 1. So to make lithium atom a stable one, it will lose one of its electron. And with that, this is the symbol. We have a bracket and here a charge of positive. Same as with the aluminum. So how it acquires a charge of positive 3. So the valence electron of aluminum is 3. When it loses 3 of its electrons, so it acquires a charge of positive 3. How? With a neutral atom, proton of 13 and electron of 13. So since it loses 3 of its electrons, so it will acquire now a charge of positive 3. Okay, so to have a stable configuration, and the last will be 8. So similar with lithium, where its outermost electron is 2, followed by the helium atom. Okay? So for negative ion formation, this time we have anion. So these are negatively charged ion. And here how an atom acquire a negative charge when they gain electrons. So with family 15, they gain 3 electrons. Okay, for these elements to have an 8 valence electron. So because their last electrons are 5, so they need 3. So they have to gain 3, so they will acquire a charge of negative 3. For family 16, we have they gain 2 electrons to acquire a negative 2 charge, and for halogens, they lose 1 electron. They gain rather 1 electron and acquire a charge of negative 1. So we have an example here for fluorine. So take note, outermost electron is 7. So it needs 1. So it will receive 1 electron to make it 8 to become stable. And with that, it has now a charge of negative 1. Same as with the element sulfur. So sulfur has an outermost electron of 6, so it needs 2 still to become 8. And with that, it gains 2 electron to have this symbol and acquire a charge of negative 2. So positive 16, negative 18 is negative 2. So this is all about negative ion formation, or for an anion. Okay, so how do we write the Lewis structure of ions? So from the examples a while ago of cation and anion, this time, let's see how an ion is represented by Lewis. So we have here for lithium, the example a while ago, losing one of its electrons. So this will be the symbol or the Lewis structure for lithium ion, a charge of positive 1. For fluorine, how do we write or how do we represent that using the Lewis structure? So fluorine with 7 valence electron this time. By gaining 1, it has now 8 valence electron. So it has bracket, and this time it has a charge of negative 1. Okay? So how are ionic compounds formed? Considering that we understand what cations are. Cations are formed by losing of electron, and anions are formed by gaining of electron. So how are ionic compounds formed? So this is formed through ionic bonding. So this is a type of bond that involves a metal, a metallic element, and a non-metallic element, a cation and an anion. It's a bond formed by the attraction between two oppositely charged ions. So the cation and the anion are two oppositely charged ions. Typical example, of course, is sodium chloride. So look how the ionic compound sodium chloride is formed. So from sodium with 1 valence electron and chlorine 7 valence electron. So sodium will lose 1 electron and chlorine will gain 1. When sodium loses electron, it acquires a positive charge, so it's a cation. And chlorine, on the other hand, by gaining 1 electron, so it has now a charge of negative, so it's now an anion. Therefore, the attraction between the positive ion and the negative anion forms the compound. So the bond that holds sodium chloride in the compound is ionic bond because it is formed by the attraction of the positive and negative. Same as with magnesium chloride. So magnesium, we know, its Lewis structure is we have 2 dots, and chlorine we have 7 dots. Okay, so magnesium, to make it stable, will lose 2 of its electrons, so it will lose 1 for each chlorine atom. So 2 chlorine atoms will receive or will gain the 2 available electrons from magnesium. So after losing electron, magnesium is now a charge of positive 2, and chlorine now is -1. So the attraction between the 2 positive and -1 forms the compound magnesium chloride. So the bond that holds magnesium and chlorine together in the compound is ionic bond. And because ionic bond are formed by the attraction of the positive and the negative, what are its properties? So first, it has a high melting and boiling point. Solids are non-conductors, but when they are molten or dissolved in water, they will now become electrolytes or good conductor because the ions move freely. They are highly soluble in water. They are solid mostly at room temperature, and they are hard and brittle. Okay, so ionic bond is so strong, and that strength, of course, uh, makes this characteristic possible. Okay. So this time we'll be moving on to covalent bond. So covalent bond is all about sharing of electrons. So what atoms share electrons? So this is formed normally by hydrogen and elements in families 4A up to 7A. Okay, so compound result from the sharing of one or more pairs. So it's not only one pair. 2 pairs are possible, 3 pairs are possible. In fact, we have 3 types of covalent bond depending on the number of pair of electrons shared between atoms. So we have single, double, and triple. So take note, for hydrogen, 1 pair of electron is shared between hydrogen atom. So it's single bond. 2 pairs of electrons are shared, it's double bond, and 3 pairs of electrons shared, it's triple bond. Okay? And for the properties, since atoms share electrons, we'll see its properties. So they have low melting and boiling point. So they are liquid or gases at room temperature. They are soft and brittle. Poor electrical and thermal conductivity, and they are not soluble in water, but they are soluble in other covalent solvents. So these properties are exactly opposite of the ionic bond. Why? Because this is merely, the compounds are merely formed by sharing of electrons. And for writing Lewis structures for covalent compounds, we call it as molecules. So for compounds formed by ionic bonding is ionic compound, but the compound formed by covalent bond, we call it as molecules. Polyatomic ions can also be under this. So how to write the Lewis structure? Now, these are the guidelines for writing LEDs of molecules and polyatomic ions. First, take note of the total valence electrons. So you have to add up and then choose the central atom. The central atom is the atom with the highest covalency number. So covalency number is the number of bonds formed by the atom. Bond the other atom to the central using single bond first. And then the remaining electron will be assigned to the attached atom before it's distributed to the central. And then take note of this if the octet rule is followed. So if there's a deficiency, we have to apply multiple bond. So if single bond will not work, you can have multiple bonding, single, double, and triple, and so on. Okay, but see to it that octet rule is followed. Say for example, for water molecule. So here, which is the central atom, obviously it's oxygen, right? So hydrogen, take note of the total number of electrons. So we have hydrogen is 1 times 2 is 2, then oxygen is 6, so we have 8. So how are we going to distribute that 8 electrons to make the covalent bond possible for water molecules? So here, first is the hydrogen will be the bonded atom and oxygen is the central. Then have single bond first for hydrogen and oxygen, so that makes use of 4 electrons. So there are still 4 electrons left, and these 4 electrons left will be distributed to the central atom. So check if the octet rule is followed. Hydrogen 1 2, here 1 2, so it's stable. Take note, hydrogen should follow the noble gas configuration of helium to make it stable, so it's just 2, and the rest will be 8. And then oxygen 2 4 6 8. Take note of the total number of valence electron. We have 8, so 8 is distributed and the 3 atoms are stable. So same as with formaldehyde, so check first the total number of valence electrons. So carbon is 4, and then hydrogen is 2, is 6, and then oxygen is 6. So there should be 12 electrons, 12 dots that you're going to use. Central atom will be, let's check, carbon is family 4, its covalency is 4, hydrogen covalency is 1, and oxygen covalency is 2. So which is the central atom now? Okay, good. So it's carbon. So place it at the middle. So this is one possible arrangement that you can give for this molecule. Then have a single bond first, bond it to the central, and how many are used? We have 2 4 6, and since the total is 12, so we still have 12 electrons. Where are we going to put that? Okay, so it's an oxygen, not with hydrogen, because hydrogen here is already stable. So let's count if it is 12, 2 4 6 8 10 12. But take note, check the octet, carbon 2 4 6. So this is still deficient in electron, therefore you have to apply multiple bonding, or single bond here will not be applicable. Okay, so let's have multiple bonding. Okay, we have the double bond. So let's count 2 4 6 8 10 12. So it's 12, and all the atoms are stable. Carbon 2 4 6 8, oxygen 2 4 6 8, and hydrogen both 2 electrons. Okay, also with nitrosyl chloride, here the total is 5 plus 6 is 11 plus 7 is 18. So use that 18 dots, distribute that 18 dots so that each will receive 8 electrons. And how will you do that? Central atom, of course, will be nitrogen. Why? Okay, because nitrogen has the highest covalency number. It's 3 covalency, 2 covalency, and 1 covalency number. So nitrogen will be placed at the middle. Using that single bond, so we make use of 4, so we still have 12. Put that first to the bonded, not with the central. So we have 2 4 6 8 10 12 14 16, so we still have 2 electrons, so we are going to put that at the central. But because nitrogen is deficient, because again, take note of the octet, we'll apply multiple bonding. So this time, let's count if there are 18 electrons. 2 4 6 8 10 12 14 16 18, and each has 8 electrons. So this is all about covalent bonding. Okay. So with this, there are actually 3 exceptions to the octet rule. And what are these cases? First, atoms with fewer than 4 valence electrons, sharing them to form covalent bond. Okay, family 2, family 3, like beryllium in family 2 and boron in family 3. So less than 4. And with that, say beryllium chloride. So here, beryllium, we cannot just put one more bond because beryllium has 2 dots, 2 electrons, and it's already shared here. Therefore, beryllium will be deficient. Okay? So we have also for elements in the higher periods like phosphorus and sulfur, like in phosphorus pentachloride and sulfur hexafluoride. So if you are to check the arrangement, the distribution, phosphorus, and then there are 5 chlorine. The chlorine are stable, but for phosphorus, it has 10 valence electron. Okay, so it's more than 8. Same as with sulfur, there are 6 fluorine attached to it or bonded to it. So sulfur will have 12 electrons. So this is another exception. And finally, the last one will be an odd number. Total is odd number, like in nitrogen dioxide. So nitrogen is 5, then 6 times 2 is 12, plus 5 is 17. So whatever arrangement you have, it will not, one of the atoms will always be deficient, okay? Because this is an odd number. So these are the 3 exceptions for the octet, okay? And of course, writing the distribution, the covalent bonding in a molecule or in polyatomic ions, we can of course determine the shape of molecules or the geometry. So what they mean by geometry? So this describes the 3-dimensional arrangement of atoms within a molecule or polyatomic ion. The arrangement. And this is based from the BSEPR theory. And what is this theory? It's a valence shell electron pair repulsion theory, and this suggests that the electron pairs around an atom assume an arrangement in space that reduces the repulsion between them. So here in the BSEPR, it describes that bonded and the lone pairs are negative centers that repel each other, and they move as far apart as possible. Okay? Whether the electron is bonded or not, lone pair or not, they are negative centers and they tend to repel to one another. And with that, they create the 3-dimensional arrangement, the 3D pattern or the shape or the geometry. And this is the basic shape of molecules. So with formula AB. So if you'll notice, this examples has no lone pairs. They are all bonded. 2 bonded to the central, like beryllium bromide. So you see, because there are 2 bonded pairs, the further distance is almost, the orientation is 180 degree. If there are 3 atoms attached to the central, like boron trichloride, so this is trigonal planar. And this will be the distances of the 3 atoms. For 4 atoms bonded to the central, it's tetrahedral shape of molecule, like silicon tetrachloride and methane. And this is the orientation, the arrangement, the 3D arrangement. For 5 atoms bonded to the center, it's trigonal bipyramidal, like phosphorus pentachloride, and this is the orientation. Plus, of course, the last is octahedral, like sulfur hexafluoride, and this is the 3-dimensional arrangement. Now, for a modified shape where the lone pair is present, in identifying the shape, it's always the bonded that counts. But having a lone pair will modify the shape, like this one. Supposedly a while ago, this is trigonal planar, but because there is a lone pair, so here is a lone pair, 2 bonded, like in sulfur dioxide. So the shape of this is bent, this one. And for 3 bonded, 1 lone pair, it's trigonal pyramidal, like in phosphorus tribromide. So this is the arrangement. The space here will tell that there is a lone pair here. And CISO for this formula, 4 bonded, 1 lone pair, like sulfur tetrachloride. Okay, so the lone pair is here, it's CISO. And for square pyramidal, 5 bonded, 1 lone pair, like bromine tetrafluoride, and this will be the arrangement. three-dimensional arrangement. For bent molecule, two banded, two lone pair like water. So take note, water is a bent molecule. Okay? And here, for three banded, two lone pairs is a T-shaped molecule like bromine trifluoride. T-shape. The lone pairs are here. And here, for the square planar, four banded, two lone pairs, xenon tetrafluoride. So this is the arrangement. And linear shape, two banded, three lone pairs like in xenon bromide. It's linear. So again, it's important that in writing the Lewis structure, take note of the central, how many are bonded to the central and how many lone pairs for you to be able to figure out the shape of molecule. Say for example, if we have carbon tetrachloride, so the Lewis structure is this one. Take note, one banded, central is C, banded are 4. So this is AB4 and the shape will be the tetrahedral geometry. Same as with beryllium hydride, two atoms bonded to the central. So this is AB2 and the furthest distance between the two is 180 and therefore it's linear. And for formaldehyde, there are three atoms bonded to the central. So this is AB3 and the shape is trigonal planar. So this is again what BSEPR tells about identifying the shape of the molecule. Okay, so the electrons repel one another and they move far apart as possible, okay, to form that three-dimensional shape. Okay, so for polarity of molecules, since covalent compounds form molecules, so there are actually two types of bond. You have nonpolar covalent bond. This is the type of bond formed when between two non-metal atoms, and here the electronegativity of the atoms are the same, so therefore it's almost equal to zero. There's an equal sharing of the bonding of electron pair, like the diatomic molecules, say hydrogen and hydrogen. So if you are to consider the electronegativity value, they are the same and sharing of electron will be the same because the atoms are the same and therefore it's non-polar. In polar covalent bond, this is between two non-metal where their electronegativities are different and there is an unequal sharing of electron. So though they share electron, there will be an unequal sharing. One is partially positive, one is partially negative. And here we describe that as polar covalent bond. Like in hydrogen and chlorine, they are both non-metal, but in the sharing, the electron favors more on the part of chlorine than the part of the hydrogen, and therefore it's non-polar. So to easily figure out the polarity of the bond, you take note of the electronegativity difference or the electronegativity value. Take note, we can find the electronegativity value in the periodic table. So if it is 1.7 and above, we classify that as ionic bond. Between 0.4 to 1.7 is polar covalent bond, and less than 0.4 below is non-polar covalent bond. So for example, for carbon and hydrogen, so you check the value of the electronegativity. So carbon is 2.5, hydrogen 2.1. So the difference is 0.4 and therefore it's classified as non-polar. So here for carbon and oxygen, so this is two non-metal, carbon is 2.5 and oxygen is 3.5. The difference is 0. So it lies here, it falls here. So it's categorized as polar covalent bond. And the last one, of course, is ionic bond, wherein for sodium and chlorine, sodium is 3 and chlorine is 0.9. So the difference is 2.1 and therefore is classified as ionic bond. So electronegativity difference will help you determine the type of bond present between atoms. Okay. This polarity of molecules, of course, determining if it is polar or non-polar, is very significant in uh, identifying if a solute will dissolve in a given solvent. Take note of the general rule, like dissolves like. What does it mean? So meaning to say, a polar solute will be dissolved in a polar solvent, and non-polar solute is soluble in a non-polar solvent. So take note of that. Okay? So meaning to say, a non-polar solute will not dissolve in a polar solvent. So you check that, you research on that, of what are the examples of polar solute and what are the example of polar solvent. So they dissolve, the solvent will dissolve the solute. Same as with non-polar solute and non-polar solvent. Okay, so that ends our discussion for this afternoon. Thank you so much for your time. I hope you learned something